All right, good morning, everyone. So first, I'll start off with the admission of a mistake, because things happen. So yesterday in the first group assignment, we wrote down, without the A here, we wrote down the intensity divided by C was equal to mg. But that's a pressure. So Derek actually helped point this out to me yesterday because he couldn't understand why he kept getting the answer wrong. So anyways, what I noticed afterward was that, yeah, so I actually only wrote pressure is equal to mg, but pressure is not a force. So to make it into a force, we have to actually multiply that by the area, where the area in this case is going to be the cross-sectional area of that little sphere up there, right? Reason for that is, again, the light is coming out, and that's what it's only going to see is the cross-sectional area of that sphere. So in this case, we need to multiply this left-hand side by pi r squared, where r in this case is the radius of the sphere, not the radius of the giant sphere that this isotropic source is sending things out. So the radius of the actual physical sphere itself. So again, to make this a force is equal to a force instead of the radiating pressure is equal to a force, we just have to multiply by that cross-sectional area. Once you do that, then the number should work out correct. Do that 10 to the 11th that I actually wrote down on the solution instead of the 10 to the 6th that everybody was getting yesterday. So sorry about that. I don't know where my brain went, but these things happen. Okay, so that's it. So I just wanted to point that out so now you can fix that and understand that little thing. So good. So next time we're going to talk about, to finish off this particular chapter, is light is polarized. So anybody who wears sunglasses will tell you that they know light is polarized, because what's the point of wearing sunglasses? To decrease the intensity of the light, right? So that way you're not seeing as much light as you would see if you were not wearing something like sunglasses. So what is the polarization of light? So the polarization of light refers to the axis at which the electric field is oscillating about. So this is what's known as the polarization axis. So the polarization axis is the axis in which the electric field oscillates. So remember that the magnetic field is perpendicular to that. So here, when we refer to the polarization of a light source, we're only referring to the axis in which the electric field oscillates about. Now, light usually comes in one of two forms. It's either going to be polarized or unpolarized. Now, typically when we're talking about in this class, what we're talking about is what's known as linearly polarized, which means light is going to stay on that polarization axis the entire time if it is polarized. There's also what's known as rotationally polarized, which means that the electric field is actually going to oscillate or go in an XY portion, which means that if I plotted, let's say this is the x-axis, this is the y-axis, what happened in that case then is that the axis of oscillation is actually going to rotate and then come back to the original rotation. Right? So this is what we call circularly polarized light. Circularly polarized. Now this will happen either one or two directions. It's either going to be right circularly polarized or left circularly polarized. All that means is the direction, is it going to go clockwise or counterclockwise? But for us, what we really care about is this linearly polarized. So for polarized light, all that means is my electric field, for example, is going to oscillate back and forth about this particular axis, for example. So this is what we call polarized light. There's a lot of sources in nature which creates polarized light. For example, when sunlight hits water and gets reflected off of water, that reflection off of water actually creates polarized light. It becomes polarized in a particular direction. Things man-made that actually create polarized light are things like TVs, antennas, things like that. We create actually polarization to go in a particular direction. So for example, here in the US, when it comes to a TV signal, we create horizontally polarized light, which is why when you put a TV antenna on your house, the bars are in this direction, in a horizontal direction. That's to make sure that you pick up the signal. In UK, we got to be different than the UK. So the UK actually does this. They actually do vertically polarized TVs and radio signals. So that's why if you go to the UK, their antennas are actually this way when ours are this way. We got to be different than the UK. Right? So these are sources of polarized light. Of course, there are also unpolarized sources, where unpolarized basically means that there is no axis of polarization. So light is continuously coming from you, and what you're going to see is that different portions of light will have polarization axes in different directions. This is what we call unpolarized light. Oops, back a little bit. So unpolarized light is light with no polarization axis. So for example, light that comes from the sun is unpolarized. So light from the sun so basically all this means is if I was looking at light coming towards me, again, assuming it's moving, say, in the z direction, in this case, we're going to have some lights oscillating along this particular axis. Some light will then be oscillating around, say, this particular axis. Some of the light will then be along this particular axis, and etc. So there's no distinct polarization axis because some frequencies and it's going to constantly change. So basically, it's going to be oscillating along every particular axis. This is what we call unpolarized light. But it turns out that we can actually take polarized light or unpolarized light and polarize it. The way that we do this is we use what's called a polarizer. So polarizer is a way that we can actually take something like sunlight, which is unpolarized, and then send that through a polarizer to then polarize it in a particular axis. So the way that this works is, what a polarizer is basically molecules which actually absorb light. Okay? So here, let's say I have a whole bunch of molecules along this particular axis. Let's call this the x-axis. And the job of these molecules then is to absorb the light in the x direction. So basically, if I take unpolarized light from the sun, let's say I'm going to draw that in yellow. So here's my unpolarized light in the sun. What's going to happen is when they interact with this polarizer then is going to have these molecules absorb all the light which is then in the horizontal direction, which means by the time the light comes out through in this particular direction, it's then going to absorb all the light in the horizontal direction, which means all the light is going to pass through only in the vertical direction. So my light which then passes through here, and if I look at this guy, my light then is going to be oscillating along the vertical axis. So in this case, we would call that vertically polarized light. So here, this would then be a vertical polarizer, or what we would call a Y polarizer. So the polarization of our polarizer tells you the direction at which the light is going to oscillate, or the electric field is going to oscillate once it comes outside of the polarizer. So this would be a vertical or a Y polarizer. Now, if I have a polarizer going from unpolarized light to polarized light, what ends up happening then is that the intensity of the light which is initially coming in, let me call that I0, reduces down to a new intensity I, where that new intensity is equal to 1/2 of the original intensity. So if I send the light through, initially unpolarized through a polarizer, automatically half of the intensity is automatically decreased. The reason for that is, again, if we go back to our picture, we can think of all of these different polarization axes as a sum of vertical portions of electric field plus then horizontal portions of electric field. Right? So they're vectors. A vector we can decompose into both a horizontal piece and a vertical piece. So in this case, since it's cutting out all of the horizontal pieces, 50% of the vectors are pointing in the horizontal direction, 50% of the vectors are pointing in the vertical direction. So in this case, automatically half of the magnitude is decreased, and if half the magnitude is decreased, that means the intensity then is also going to decrease by a factor of 1/2. Is okay with this? Now, what happens then if I send through polarized light through another polarizer? So let's say I start off with polarized light going in this direction, and I'm going to pass this through then a polarizer. What happens then to the intensity of the light as it passes through? So what I want to know then is this comes in with an intensity I, let's call this I1. What then happens to the intensity when it comes through? Let's call that guy I2. Well, the answer to this is it actually depends on how the polarization axis of the original light is relative to that of the polarizer itself. So let's draw kind of a picture. So let's say that here, my light is initially polarized along this particular axis, and I'm just going to call this some angle theta. And let's say our polarizer is going to let light through then in this particular direction. So in the horizontal direction. Now, what we know from the pointing vector, remember the pointing vector said that the intensity was proportional to, this way, the electric field times the magnetic field. But we also know that the speed of light is equal to the electric field divided by the magnetic field, which means that our intensity is also then proportional to the total electric field squared. Okay with this? So here all I'm doing is I'm replacing B with E over C, but since I'm only doing proportional, I don't care about that C factor. I just want to look at the electric field squared. So what that says then is that what? To know how the intensity changes, all I have to do is know how the electric field changes. So initially, my total electric field is along this particular axis, but once it passes through then the polarizer, only this portion of the electric field is going to pass through. So according to this, our beautiful picture here, this is my initial electric field, and the electric field which is going to pass through is only going to be this portion, which is going to be an initial electric field times cosine of the angle between the two. Which means then that my final intensity, which is then proportional to the electric field squared, is then going to be equal to the initial electric field squared times cosine squared of the angle. That is proportional. But the initial electric field squared is actually then just the initial intensity. So this thing is actually just equal to the intensity times cosine squared of the angle between the two. So what this says then is that what? If my initial intensity, which is coming through, is I1, then after it passes through the polarizer, I then have another intensity, or it has decreased in the amount of intensity from the initial intensity by cosine squared of the angle. Where this angle then is the angle relative between the original polarization axis and the axis of the polarizer. So this is my angle between the two. Okay with this? So what would then happen if these two are at a 90-degree angle from each other? So if my initial light was coming in vertically polarized, my polarizer after that then is horizontally polarized, how much intensity would I have passing through? So what would the angle be between the two? So if initially it's this way, afterward it wants to go this way, what's this angle? 90, good. What's cosine of 90? 0. What's 0 squared? 0. So what this says then is that what? If the angle between the two, so if I initially start off with vertically polarized light, I try to send that through a horizontal polarizer, the intensity of the light would go to 0. I would have no light actually passing through this polarizer. To show you that, I'll show you this little video, okay? So what I have here is this guy is simply a polarizer. So here you can see my shirt. You can also see the computer. Hopefully it doesn't screw too much. But anyways, you can kind of see the light reflecting off of me is dimmer here, meaning the intensity is less than it is reflecting off my shirt here. So all I'm going to do from here then is hold up a second polarizer in front of this and then slowly change the rotation axis. And we'll see what happens. A lot of noise. Good. So there's a second polarizer. Actually hold it the correct way. There we go. So there are the two. So as you turn it, see now we see absolutely nothing. Somewhere between you can still see my shirt. Rotate it the other way. Again, you get absolutely nothing. See my shirt again. And now you get nothing. So if I have two consecutive polarizers, one is rotated from the other one by 90 degrees, no light will actually then pass through this particular polarizer. So this thing here, once it comes back up, is called Malice's law. So Malice's law says that the intensity through the second one is equal to the intensity from the first one times cosine squared of the angle between the two. This guy's called Malice's law. So Malice's law, again, is when I take polarized light, send it through a polarizer, and then this is the amount of intensity I get through it after it passes through. But again, if I send light through, or unpolarized light through a polarizer, regardless of the orientation at which it is, I automatically decrease the intensity by a factor of half. Okay with this? So, these are polarizers. So let's do an example of a polarizer. So this says I have initially unpolarized light that's sent into a system of 3 polarization sheets whose polarization directions make angles theta 1, theta 2, theta 3, which are all equal to 50 degrees, with the y-axis C below. So here, this is theta 1, this is theta 2, and this is theta 3. So I want to know what percentage of the initial intensity is transmitted by the system. So good. So again, initially, I have unpolarized light coming in through this polarizer. That then is going to send intensity through this polarizer. I'm going to have more intensity come through this polarizer. And then finally, I'm going to have this final intensity. So we want to know what is the ratio then of the final intensity I3 to that of the initial intensity I0. Okay? Good. Let's talk about this. So let's draw our picture. So here is my initial. Let's call that I0. That's going to pass through this polarizer, where this one has an angle theta 1 relative to the vertical. This light then is going to come out. This is going to have an intensity I1. That's going to go through a second polarizer, whose angle relative is down here. So this is theta 2. Finally, this one's going to come out, I2, and then go through a third polarizer, whose angle relative to the vertical is this angle, theta 3. And then finally, that's going to give me, let's do it in gray, this I3. Okay. So what we want to do then is figure out what is I3 relative to I0. And then take the ratio of those guys. So let's talk about each polarization as it goes through. So what happened here is, again, I'm starting off with unpolarized light here. So this is unpolarized. I'm going to send that through a polarizer. So as we already talked about, what we know is that the intensity I1 is automatically 1/2 of the initial intensity. So anytime I take unpolarized light, I pass that through a polarizer, automatically that will decrease the intensity by a factor of 1/2. So that was nice and easy. So I1 is simply 1/2 of I0. So now what's going to happen is the light which is moving here in this direction is going to be polarized along this line here. So it's going to be oscillating along this theta 1 direction. I'm then going to pass that through this polarizer, whose polarization axis is along this axis, which means I2 then is going to decrease from I1 by cosine squared of the angle between the two. So what's happening here is this light coming in is polarized along this axis, theta 1. I want to polarize it along this axis, theta 2, which means this angle here is the angle theta between the two. Okay? So now we can say, well, I2 is equal to I1 times cosine squared of theta, where theta is equal to 180 degrees is equal to theta plus theta 1 plus theta 2. Okay? So theta then is equal to 180 degrees minus theta 1 minus theta 2. We'll plug in those numbers in a second. So now what's happening is I2 has light which is now polarized along theta 2, which means by the time it interacts with polarizer 3, the light now is polarized along this axis of theta 2. So now my light is polarized along this axis. I want to polarize it now along this particular axis, which means that the angle between the two of these is this angle, and I'm going to call that the angle phi. So Malice's law now says that I3 is equal to I2 times cosine squared of phi. Okay. Where according to our picture, phi then is equal to, again, 180 degrees minus theta 2 minus theta 3. Okay? So let's put everything together. So finally we can say I3 then is equal to I2, but I know I2 is equal to I1 times cosine squared of theta times cosine squared of phi. But I also know I1 is simply equal to 1/2 of I0. So cosine squared theta, cosine squared of phi. Plug in our stuff, this becomes 1/2 I0 times cosine squared of theta 1 plus theta 2 times cosine squared of theta 2 plus theta 3. Okay with this? Good, but what's cosine of 180 minus something? It's negative cosine of that same angle. So if I did, good question. So if I did cosine of 180 degrees minus theta, that's equal to negative cosine of theta. But since I'm squaring that cosine, that negative goes away and I don't care. So for our case, we had cosine of 180 degrees minus theta 1 plus theta 2. So that's the same thing as negative cosine theta 1 plus theta 2. Okay? What's up, Dylan? I'm sorry?
They're just 80, so 100
You're good? Okay. Good. So finally, I have I3 divided by I0 then is equal to 1/2 cosine squared of theta 1 plus theta 2 times cosine squared of theta 2 plus theta 3. Look at my numbers. What I find in this case then is that this works out to be 4.5 times 10 to the minus 4. So basically what this means then is that what? The final intensity is 4.5 times 10 to the minus 4 times the initial intensity. So it's dropped off by a lot. Molly. Yes, yeah, because in this case theta 1 is equal to theta 2, which is equal to theta 3, so that's just 100. So in this case this is, actually these two terms are the same. So this is actually the same thing as cosine to the 4th of 100. But yes, I just used 50, 50, and 50. So the same thing as 1/2 of cosine to the 4th of 100. So make sure you're back in degree mode and not radian mode. Otherwise, you're going to get a completely wrong answer. That's what we're doing. Okay? So these are polarizers. So again, light is polarized. Polarization of light just means the axis at which the electric field is oscillating about. Again, we can actually change the direction of polarization based on the fact that we can send them through polarizers. And one little thing I want to talk about, not to confuse you too much, but it's pretty cool. We're not going to do any math about this, but it turns out that if I took a Y polarizer here, and I took an X polarizer here, which we now know the intensity by the time it would come out here would be equal to 0. Right? Because what would happen here is that the light coming through now would be only vertically polarized. And I'm trying to send a vertical polarization through then an X polarizer and now get 0 intensity. But something which is pretty cool, what happens if I take a third polarizer and I put it in between these two polarizers? And let's say I take a polarizer that's orientated about the 45-degree line. So let's say this is 45-degree polarization. What happens now? What happens to the intensity of the light down here? Will it still be equal to 0? The answer is actually no. If I put in this polarization of a line of 45 degrees, what happens in that case then is this no longer kills off this particular polarization here. I'm now going to have a non-zero intensity actually pass through. So by putting in a third polarizer halfway in between the two, or at least somewhere in between the two, what that does is it's actually going to take this Y polarization, force it now to be along the 45-degree line, which means by the time it comes through here, I now have a little bit of non-zero horizontal portion of the electric field, which means that you can actually disturb this to now create a non-zero intensity. So even though the Y and the X should give me 0, but once I put in that 45, that now is going to destroy that, which now makes it so it's not going to be 0 intensity anymore. Again, the reason for that is because the electric field is for superposition. So this electric field here is a superposition along the 45-degree line, which means when it comes through the 45-degree line, it's also a superposition of vertical and horizontal, which means that it's going to be non-zero by the time it comes through. Turns out, which is the most interesting thing, this happens with subatomic particles as well. So you can actually take what are known as Stern-Gerlach apparatuses, which you can cause the spin of a particle to point in a particular direction. So if you have a point along the Y direction first and then along the X direction, same thing, you're going to have a 0 intensity coming through. But again, if you take an intermediate polarizer, you can actually cause it to be non-zero by the time it comes out through. So this is all quantum mechanics. So basically, subatomic particles act exactly like light does, which is the basis of quantum mechanics, which is actually kind of interesting. But anywho, I think that's interesting. So let's now do a group assignment. So I'll give you a quick group assignment on all these guys. So that we've seen polarizers. So this is very similar to the one we just did. So where are you? There you are. So this says we have an unpolarized beam of light with an intensity of 43 watts per meter squared is sent into a system of 2 polarizers in this case, with polarizing directions of 70 and 90 degrees relative to the y-axis. So theta 1 here is 70 degrees, theta 2 here is equal to 90 degrees. So I want to know what is the intensity of a light transmitted by the system. So again, here is this unpolarized light going to pass through here. So this is going to be I1 worth of intensity. Going to come through here. This is going to be I2 worth of intensity. So we just want to know what is I2. So this I here is actually I2. So what is the final intensity as this thing actually passes through? Nice intensity. Well, you got to figure out the angle. The axis is not just the correct. So we have to do. So when it comes out through the first one, it's obviously 70 degrees. Then when it goes to the second one, it's at 90 degrees. Cosine squared. No, I still got the right answer. Just 90 minus 7. Yeah. So in this case, we don't have the 180 because we're creating a vertical axis something in there. But yeah, now here, once it passes through the first one, it's oscillating at 70 degrees. That passes through the second one, it's oscillating at 90 degrees. So the answer is going to be just. Well, yeah, either way it doesn't matter. But yeah, but here would be a positive 20 because the angle between the two is just. So it doesn't. So you switch. It'd be the same intensity. Right, because it goes as a cosine square. You're right. So negative cosine. Well, negative cosine. Cosine and negative angle is still positive. So unit axis is change. Sine of a negative angle is negative cosine. Oh, gotcha. Yeah. Ultimately doesn't matter. It's cosine. And it's squared. So. Oh, so we don't. That's still right. All righty, so it looks like everybody's doing well with that. So we're done with that chapter. Life is great. So now we're going to start the next chapter. So the next chapter still wants us to focus on the wave nature of light. So basically we're going to start talking about some of the cool and interesting things that happens when you consider the wave nature of light. When we're done with this chapter, we'll then start looking at more of the geometrical things that happens with light. So that's when we start looking at optics and things like that. But in this chapter, we're going to talk specifically about the wave nature of light. So let's talk about a wave. So let's say if I had a source, and here's my source. What happens is if I had a source, this thing creates spherical waves, which then propagate outward at the speed of light. So here is my wave moving outward at the speed of light. So what happens is as it moves further and further and further, these spheres are going to become bigger and bigger and bigger until eventually we're going to make it way out into this region here, where these spheres are going to become so large that it's going to look like the radius goes to infinity, which means that these things are going to become effectively plane waves. So out here, we're going to have light then moving, say, in this direction at the speed of light. So these are the wave fronts. So these parts here are the wave fronts. And this is what we're going to call the far field or radiation region. So basically in this region, what happens is these spherical waves turn then into what are called plane waves. So here these guys are plane waves. Now, what's interesting kind of about plane waves is that, well, any waves in general, is that waves will actually cut around corners and go through areas and do all kinds of cool things. And this is because of what's known as Hegens Principle. So what Hegens Principle says is that even though I have a wave front, so let's say here's my wave front, what you can think of is that the wave front is actually created from a whole bunch of spherical or point sources. So each one of these dots is a point source. And each one of these point sources then is going to create a spherical wave, which is going to move outward at the speed of light. So each one of these guys are going to move in all different directions at the speed of light. But what happens is if I go from time is equal to 0, so let's call this is happening at time is equal to 0, to some later time, t is equal to say t1, what happens is each one of these spheres get bigger, and then I get the interference between the waves of each one of these spheres, as we talked about interference a long time ago. And what happened then is that the interference between each one of these waves will again create a plane wave. Right? So if I think about at time is equal to 0, each one of these waves is getting bigger. So what happens at this case then is I'm going to create another plane wave, still moving in this direction at the speed of light, but this is created by the interference between a whole bunch of spherical waves that are all basically doing something like this. Then at this time, I'm now going to create a whole bunch of new point sources, which are also going to create spherical waves, and the process is going to repeat. Okay? This is called Hegens Principle. So Hegens Principle says that even in this far field region, each one of these different points acts as a point source, creating spherical waves. At some later time, all of these wave fronts from these spherical waves will interfere with each other, creating a plane wave still moving in exactly the same direction. Now the question is, what happens now if this plane wave interacts with something like a corner or something which has a hole in it? Right? So let's say this is moving to something which looks something like this. So let's say I put a shield here or a slit, and I want to know what happens to the wave at this slit. Well, what happened is by the time it gets here, only some of these plane waves or some of these point sources are going to exist in this region, creating plane waves which are going to move out, which means that what? As it starts to go further in time, this thing is not going to create a plane wave anymore, but again, it's going to create now more of a spherical wave. The spherical wave is now going to move away from the source and do something like this. This is what's known as diffraction. So the encounter of a plane wave with some sort of slit or some sort of blockade creates now a spherical wave, which is now going to move away from it. So let me show you somebody else's picture, since my drawings are always so fantastic. So basically we're talking about this. So here again is our Hegens Principle. So here each one of these point sources are creating a spherical wave. Interference between those creates a new wave at some later time, which again is a plane wave. But if I interact that plane wave onto something like a slit, what will happen then is I get dispersion and diffraction. Now it turns out that, again, this is the picture I was trying to draw. So here I'm blocking all of those different regions from the plane wave. So I only have certain points inside of the middle region here, which is creating point sources. So what happened is I'm going to create these spherical waves, but it's not going to move as a plane wave anymore. It's going to create a spherical wave. Now it turns out that the size of this blockade matters. So if the blockade here is, let's say this has a slit width of about A, if A is much, much bigger than the wavelength of the wave itself, I'm not going to get much diffraction. This thing is going to still be kind of like a plane wave, but only in a small single collimated slit. Okay? So I'm going to get a collimated beam. But if the size of the width here is approximately the same size as the wavelength of the wave, what will happen is this, I'm going to get a lot of dispersion. I'm going to get a lot of diffraction here. Right? So Let's write that down. So what this thing says is, again, if my slit here, call that size A, this has a width of A. So if A is much, much greater than lambda, we get very little diffraction. So basically, this is just going to give us a collimated beam. Diffraction. I know how to spell. There we go. However, if A is approximately the same size then as lambda, we're going to get a lot of diffraction. I mean, the diffraction then is going to give us basically a column of waves moving out doing something like this. Now, why is this important? Well, this is important because I can actually create interference between waves that are moving through two slits. This is what's known as the Young's double slit experiment. Let's talk about the Young's double slit experiment. So Young's double slit experiment was the experiment that basically showed definitively that light was actually a wave. Up until this point in time, people had conversations, they agreed and disagreed with each other. They actually got into fistfights about who was correct, whether light was a particle or a wave. Newton himself thought that light was a particle. He called them corpusculas. So in this case, he thought they were little tiny particles like photons, which actually carried the light, and that they were actually particles. Other people, like Hegens, thought that they were actually waves. In that case, it was waves which were moving kind of like water waves, and the Young's double slit experiment with diffraction basically definitively showed that light was actually a wave. Fast forward about half a decade later, quantum mechanics comes around and says, well, no, it's actually both. It's a particle and a wave simultaneously. That's a whole other story that we're not going to bother talking about. So, but this was the experiment that finally put the nail in what everybody thought was the coffin of who was correct. So the way the Young double slit experiment is basically this. So typically you don't use sunlight, you use more laser light. You want something that's a lot more coherent, and we'll talk about why that happens to be. But anyways, you're going to take that, send that through a single slit that causes some sort of diffraction. Now you're going to put that into a double slit, where now you're going to get diffraction through both of the two different slits. And then what ends up happening is these two slits will create spherical waves. As we talked about way back when we did sound waves, we're going to get constructive and destructive interference along the points of this, depending on if they're in phase or out of phase with each other. And then you shine that onto a screen, and then what ends up happening is you get what's called a diffraction pattern. So from here, you're going to see some light spots, dark spots, light spots, dark spots, light spots, dark spots, as they're going to interchange with each other, which is only possible if the two waves are actually superimposing on top of each other, i.e. interfering with each other. So if you look at the screen, you're going to see something that looks like this. So again, light spots, these are where you have constructive interference, dark spots where you then have destructive interference, all coming from the fact that light is impingent onto these two different slits, which are then creating interference patterns from the diffraction of the light. Again, this is only possible with light being a wave, not a particle. If it was simply a particle, you would have two beams here. One would just hit here, the other one would hit here. You would have two clumps of intensity, and that's it. You would have no interference pattern to it at all. So this is what we call the Young's double slit experiment. As I said, this was the most important experiment that finally showed that definitively light was a wave, not a particle. But again, quantum mechanics had to go and screw that up later. Well, that's fine. Light is great. And the one that actually screwed it up the most are two. One's called the Compton effect, and the other one is what's known as the photoelectric effect. Anybody know photovoltaics? So solar cells? Heard of these things before? Don't see them on buildings every once in a while. There's a whole photovoltaic farm in the northern part of Evansville. Solar panels, solar cells, trying to contain free energy. Where have you guys been? Never mind, I won't talk about that. So anyways, both of those two actually showed that light is actually a particle, not simply just a wave, but anyways. So what's happening here again is that these guys are interfering depending on what we talked about way back when in chapter 17, path length difference. So we're going to return back to all of that different stuff that we saw before. So you can actually explain where you're going to see these lit marks and where you're going to see these dark marks via path length difference. So let's remind ourselves what path length difference said. So Young's double-slit experiment, again, was the experiment that showed light is a wave. So here we can explain all of this via path length difference. So what does path length difference say? So remember that path length difference said that the difference in the two lengths, let's call this delta L instead of delta D in this case, I think before we called it delta D, is then equal to one of two things. So this is equal to either n times lambda, if we have constructive interference, and then n plus a half times lambda if we have destructive interference. This is our path length difference. So let's think about our plane waves here. So let's think about our Young's double-slit experiment. So here are my two slits. Okay? So let's call this slit 1 and slit 2. And this is going to be my screen. So let's choose some point. Let's look at this point here. Let's say this is the point we're going to look at our interference. So what happened then is this guy here is going to move across here and reach this particular point. And then this one here is going to move here and interfere with this guy at that particular point. Okay? So meaning that this one here is path 1. So this is path 1, and this guy here is path 2. Now let's also say that these two slits are separated by a distance of little d. So this is little d. So notice here, if I drop a perpendicular across here onto this point here so that this reaches perpendicular on here, what'll happen then is what? This path of 1 then will exactly equal the path length of 2, which means the only difference between path length 1 and path length 2 is this little portion here. This is my path length difference between the two. Okay. So this little tiny portion here is going to be delta L. Now, here I'm making an approximation. What I'm saying here, to make this a little more sense to you, is the distance from the slits to the screen I'm calling D, and we're assuming that D here is much, much bigger than little d. Which means even though I'm drawing this to be bigger, these two lines look like they're actually doing something like this, but in reality, D is going to be something that's like nanometer size. Capital D is going to be something that's like a meter, which means that these two lines are basically going to be moving parallel to each other. Okay, so that means then that length 1 here and length 2 are only going to be separated by this little tiny distance of t. Okay? So look, the other thing is, let's define this angle here. So let's call this angle theta, which means that here I'm creating a right triangle. So I have this side of delta L, I have this side here, and then I have this distance here, d, which is actually the hypotenuse of my triangle. So according to this angle then, since this is the hypotenuse, this is the opposite side, what this tells me then is that delta L is actually then equal to d times sine of theta. So in the Young's double-slit experiment, all this means then is that the path length difference delta L, which is equal to d sine of theta, is then equal to either n lambda for constructive interference, or n plus a half times lambda for destructive interference. So using this, we can then determine exactly where all the locations are for each one of these bright spots and dark spots. So if I'm looking for the bright spots, I'm simply going to use the constructive interference here. If I'm looking for the dark spots, I'm then going to use the destructive interference. What is n? So n corresponds to each one of these different things. So here, if I drew my interference pattern, so here I'm going to get a big central portion. That's called the central maximum. And I'm going to get this part here, this part here, this point here, this here, this here, this here, and this here. So this central part, this one is the n is equal to 0 construction. So this is my n is equal to 0 constructive interference. This then is my, what I call central maximum. This portion here and this portion here then are the n is equal to 0 destructive interference. So this is n is equal to 0. This is also n is equal to 0 destructive interference. This one here, I use a different color. Red looks good. This one here and this one here are then the n is equal to 1 for the constructive interference. And then this portion here, this portion here are then the n is equal to 2, or sorry, n is equal to 1 for destructive interference. Sorry about that. There we go. And then this one here, when I used red before, this is my n is equal to 2 for constructive. This is also n is equal to 2 for constructive, and so on. So what each one of these n's are is it's basically classifying which one of these peaks that I'm looking at. N is equal to 0 for constructive means this is the location of the central maximum. N is equal to 0 for the destructive tells me the first location that I'm going to find destructive interference. So these are my first dark spots. N is equal to 1 then is the next constructive interference, and so on. So each one of these n's then corresponds to which one am I actually talking about. So we'll pick up from here on Monday. So not too much more to talk about with this. And then from there, we'll start looking at what's known as thin film interference, which is some cool stuff. Thin film interference is what happens when you look at the mixture of water and oil, like when you're walking in the parking lot and you see in the oil, you see that rainbow type color. That's called thin film interference. So we'll talk about that. And when we're done with that, that'll be the end of this chapter. Because I forgot to bring them with me again. They're sitting on my desk in my office, and I looked right at them this morning. I was like, I got to put those in my bag so I don't forget. And then I got distracted doing something else, and then I forgot. Like I told myself I wasn't going to forget, and then I was hoping nobody's going to bring that up, so I wouldn't have to tell you that. But that's fine. Thanks, Molly. You too. Have a good weekend, everybody.